Okay, I'm back. I'm sorry about that. I had to stop and do something. So we are on this example number 3, and I got it to the point where I'm ready to put my negative infinity in for A. And so I'm just going to put negative infinity in so we can analyze what we would get here. And I would get -1 plus, and let's look at this as infinity over e to the infinity, plus 1 over e to the infinity, sorry. Oops. Remember, e to the infinity is super uber large. It's way larger than just infinity itself. And so that means that this denominator is growing super faster than the numerator. And so both of these terms are going to 0. So this becomes just plain old -1. And so therefore it converges, because it does equal just a finite number. Example number 4, I'm going to move down to this blank page. This is negative infinity to positive infinity integral 1 over 1 plus x squared dx. I do want you to think about, are there any x values that would give you division by 0? And if you would think about that, you would need this x squared to be a -1. And there's no way that I can put a any x in, square it, and get a -1 there. So therefore, the domain for this would be negative infinity to positive infinity, so we wouldn't have to worry about any vertical asymptotes or anything like that. And since we're trying to get the area under the curve for the entire function from negative infinity to positive infinity, you just need to choose a value where you can break this up, and I think 0 is a good one to choose. It seems like it's right there in the middle. Plus, when you do your integration, you put your values in. A lot of times 0 is easy to put in. So I'm going to break it at 0, but I still have to change these to limits because I still have that negative infinity here. So this is going to change into a to 0. And I still have that positive infinity on this one, so this is going to be 0 to b. And we go ahead and do this integral, and then we'll do our limit last, like we've been doing. So this is inverse tangent. So this is going to become inverse tangent of 0 minus inverse tangent of a, using that fundamental theorem of calculus. Limit as b goes to infinity. This is going to be inverse tangent of b minus inverse tangent of 0. The inverse tangent of 0 is 0. If you're thinking about it, you know that tangent is equivalent to sine over cosine. And if I was right here at 0, this is the point on the unit circle, 1 comma 0, cosine comma sine. So the tangent at 0 is equivalent to the sine at 0 over the cosine at 0. And so this would be equivalent to 0 over 1, which is 0. So it's like, when is the tangent 0? So inverse tangent of 0 is actually at 0, okay? The angle is 0. So this one goes to 0, and that one goes to 0, okay? So this gives us the limit as a approaches negative infinity of negative inverse tangent a plus the limit as b approaches infinity of inverse tangent b. Now, I also want to remind you on this problem what tangent looks like. So if I was going to just sketch a graph of tangent, I would remember that there is a vertical asymptote at pi over 2 and at negative pi over 2, and that my tangent function looks something like that. It's 0 at 0, at pi over 4, it's 1, and at negative pi over 4, it's negative 1. Okay, so that's your tangent function. So then that takes us to the inverse tangent function. So remember on inverse tangent, here, these are ratios. And, I'm sorry, I said it backwards. Here, these are angles. Sorry. And your answer to the tangent of an angle is a ratio, okay? Where here, the inverse tangent is the ratio and your answer is the angle, okay? So when you graph inverse tangent, your x values can be anything. So here, your x values were limited between negative pi over 2 and positive pi over 2 in this picture that I drew. And your y values were negative infinity to positive infinity. But they're going to switch for the inverse tangent. So your x values for inverse tangent are going to be negative infinity to positive infinity, and your y values are going to be negative pi over 2 to positive pi over 2. So there's going to be, instead of vertical asymptotes, you're going to have horizontal asymptotes for inverse tangent at negative pi over 2 and positive pi over 2. And your function looks like this. Okay? So why am I saying this or reminding you of this? Because as you put values in for, I'm going to say approaching negative infinity for that inverse tangent, that means you're putting x values in, and look at what your inverse tangent is approaching as you go. It's approaching negative pi over 2. So this becomes minus a minus pi over 2. And then as you're putting, your b's in and you're approaching infinity, you're putting all these x values in, and it's just, going to go, it's approaching positive infinity. I'm sorry, positive pi over 2 as your x approaches positive infinity here, okay? So you end up with positive pi over 2 plus positive pi over 2, which is pi. And so this converges. That example 4 converges. It's pi. Okay, let's go back up here and look at number 5. Sketch this function. And if you notice, it says over 0, 5. But I noticed right away that I cannot put that my x minus 2 has to be greater than 0. It's in the denominator, so it can't be equal to 0. So that means x has to be greater than 2. And so there is actually a vertical asymptote there at 2. So I'm going to put that vertical asymptote in. And then if I put a 3 in, I get 1. If I put a 4 in, I get 1 over root 2. Put a 5 in, I get 1 over root 3. So this function goes like this. It approaches that 2, and then it approaches 0 here. And so if I was looking to solve the integral from t to 5, I could just pick anywhere to be t. Okay, let's say I pick that to be t. This is a finite value from t to 5, okay? So when I solve this, and actually, I'm sorry, I forgot A. Why would this be considered improper? Well, because as x approaches 2 from the right, f of x goes to infinity. That's why we have, there's that vertical asymptote there with that function approaching infinity like that, is why it is this integral from 2 to 5, 1 over square root of x minus 2 dx is improper. Okay, so it is improper. So what they're having you do for part B is they're saying, well, what if we just decided that this was some value t? And we would have to say t would have to be greater than 2, right? Then what would this integral be? And so we would look at this as the integral from t to 5 of 1 over the square root of u du, because if I made my u x minus 2, my du is just dx. So I just substituted my dx with du. And so this is the same thing as the integral from t to 5 of u to the negative 1/2 du. So that's going to be u to the negative 1/2 plus 2/2. So that's u to the positive 1/2. And then divide by that, you get 2. U to the 1/2 from t to 5. Wait a minute, though. This is funny because on the last video that I just deleted because people came in and interrupted again, I didn't forget this. But on this one I did. I forgot to change my limits of integration. Don't do that. So my limits of integration here would have been for u, t minus 2 to 3. T minus 2 to 3. Let me erase that. And so this is going to be 2 times the square root of 3 minus 2 times the square root of t minus 2. So this is your integral as long as, comma, t is greater than 2. Okay? It can't equal 2. If it equals 2, then it's improper. So now they say, well, find it if t is approaching 2 from the right. Okay, so since I know that my s of t is equivalent to this 2 root 3 minus 2 root t minus 2, I'm going to substitute that in. And then when I use my substitution, 2 times the square root of 3 minus 2, when I put a 2 in here, I get the square root of 0, right, as it's approaching it. So this whole thing is going to 0. Even though it won't be 2, it would be like 2.00001 or something, but it's getting so close to 0 that this thing is going to approach 0. So 2 times the square root of 3 minus 0 is 2 times the square root of 3. So this is actually converging. Basically what we did here is we solved this improper integral. We just did it a little bit differently. We called that a variable, and then we looked at the limit as that variable went to that 2. So it's the same thing as what we're going to be doing when we solve these that have a vertical asymptote. And so it goes and, talks about these different cases again, but you need to think about, like, if this is ln x that I'm trying to find the area, and you say, wait a minute, 0, there is a vertical asymptote. I can never put 0 in, right? My domain for this y equals ln x does not include 0. It's everything, from 0 to infinity. But your value has to be greater than 0. So this is where we're like, danger, danger, we've got to replace that. So we're going to replace this, the limit as a goes to 0 from the right. And then this is going to be integral a to 1 ln x dx. And anytime we have ln x in an integral, we got to use integration by parts, and we make our u ln x. Our du is going to be 1 over x dx. Our dv is going to just be dx, so our v is x. So when we solve it, we're going to get u times v, which is going to be our x ln x minus the integral of v du. So x times 1 over x dx. And this is a integral where I need to put my, a to 1 in, right? And this actually, is from a to 1. But I'm just going to put it on this one and then put it on the end. This is just dx after the x's cancel. Limit as a goes to 0 from the right, x ln x minus x from a to 1. And I've got another sheet of paper here. So the limit as a goes to 0 from the right, this is going to be 1 times ln 1 minus 1 minus a times ln a minus a. This one's really weird to understand. Ln 1 is 0, so this becomes negative 1 minus a ln a plus a, because I just distributed my negative there. And so the only thing I can show you is if you put values in, and by the way, this does need to have an absolute value sign on it. I'm sorry that I didn't put that. This does need to have an absolute value. That needs an absolute value. So when I put this 0 in, I've got negative 1 minus. Now remember, you're approaching values that are going to be very small. So you're approaching it, it's going to be like 0.00001 or something like that, times the natural log of the absolute value of 0.00001, right? Plus 0.00001. So this obviously is approaching 0, and we don't have to worry about it. But the one that kind of is weird is this one. So if you put this in your calculator, you will see that this one is approaching 0. And what ends up happening is this thing ends up converging to negative 1. Okay, so go ahead and put that in your calculator and look to see what that value actually does. You should see that it's going to 0. It'll give you like 1.4 something e to the negative 4. Well, that's like 0.00014, right? So that one, you'll see that it's approaching 0. And so that this ends up being approaching negative 1, and it converges. Okay, so that's your example number 6. Example number 7, look at what your domain for this function would be. Negative infinity to 1 union 1 to infinity. It has a vertical asymptote at x equals 1. And look, from 0 to 3, that is a problem, because at 1, you have to split it up. And at 1, your function is approaching infinity and negative infinity. So you're coming in, so that discontinuity, you're coming into 1 from the left. So your b, you want to approach 1. Oops, I almost put right. You want to approach 1 from the left. Okay, for 1 over x minus 1 dx. And then you want to approach it from the right on this side. Oops, I forgot my limit. Sorry. It's easy to do. Limit as a goes to 1 from the right. So this would be a to 3. So we have to replace where our vertical asymptote is. Okay, you had to split it at your vertical asymptote, split this original at your vertical asymptote, and then put your values in, approach 1 from the left, approach 1 from the right. So now, this is an easy integral limit as b goes to 1 from the left. This is just going to be ln absolute value of b minus 1 minus ln absolute value of 0 minus 1. So there's that one, plus limit as a goes to 1 from the right. This one is going to be ln absolute value of 3 minus 1 minus ln absolute value of a minus 1. So you'll be taking that limit. And I think I'm going to move down here because I'm running out of space there. So we've got the limit as b goes to 1 from the left, ln absolute value of b minus 1, and then this is going to be ln, this up, I'm up here now, trying to bring it down, so I'm right there, and oops, this is going to be 0, ln of 1, right? And that's ln of 1 is 0. So plus limit as a goes to 1 from the right, you've got ln 2 minus ln absolute value of a minus 1. So that one, you still had a value. So now think about coming in to 1 from the left. Okay, you're like, I don't know, 0.9999. That's coming in from the left, right? So we're going to see what that gives us. This is going to be ln of the absolute value of negative 0.0001. Okay? And then this one is going to be ln 2 minus ln absolute value. This is going to be like 1.00001 minus 1. Okay, so plus ln 2 minus ln absolute value 0.0001. Let's just take so that they're similar. But they don't have to be, though. Maybe we shouldn't make them similar. Maybe we should make them like that. Okay, because they might not be. What ends up happening, remember what your ln is. It looks like this. If I put a value in here, my answer is going to be way to negative infinity. And if I put, an answer in here, again, it's going to negative infinity. Now, if any of your answers are negative infinity in the real number system, so if you get negative infinity here or here, this thing diverges. Okay, even though it almost looks like, wait a minute, this is negative infinity and positive infinity, they're going to cancel, I get ln 2. It doesn't work like that in the real number system. If any of these answers go to infinity like that or negative infinity, then your limit is going to diverge. Okay, so therefore, the answer to this diverges. There is in upper level mathematics with complex numbers an answer, a Cauchy principle, where your answer is ln 2, but this isn't actually a divergent limit, okay, or integral. This is a divergent integral. So that is our answer for that last one. So some of these are kind of, funny like that, but for the most part, you should have the gist of this lesson, and you should know when